So in section 8.1, we talked about representing vectors using drawings, but these can be inaccurate and kind of confusing, especially when we talk about, say, three-dimensional vectors. So in cases where more accuracy is necessary or where the system is more complicated, we can perform operations on vectors algebraically. Vectors can be represented algebraically using ordered pairs of real numbers. For example, the ordered pair 3, 5 can represent a vector in standard position. That is, its initial point is at the origin and its terminal point is at 3, 5. So in my terribly drawn coordinate plane here, the initial point is at the origin, and the terminal point is over 3 and up 5, and so this would be the vector. You can use the Pythagorean theorem to find the magnitude of a vector expressed as an ordered pair. So again, if this is my vector, 3, 5, I can make this into a right triangle, with one side being 3 and one side being 5, and then I can use the Pythagorean theorem, and the magnitude of the vector is just the length of the hypotenuse of this right triangle. So the magnitude of this vector is the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25, which is the square root of 34, which is going to be a little bit less than 6. 5.8. That's the magnitude of the vector. Very easy. Write the ordered pair that represents the vector from -3, 5 to 4, -2. Then find the magnitude of vector x, y. So it's helpful to sketch a picture here. If we sketch a picture here, we can see that this vector is going to go 1, 2, 3, 4, 5, 6, 7 in the x direction, and 1, 2, 3, 4, 5, 6, 7, -7 in the y direction. And so the vector would be 7, -7. You can also subtract the coordinates. You have to do the y minus the x because the order matters. But if you do 4 minus -3, that gets you 7 for the x, and -2 minus 5 gets you -7 for the y. So you don't have to draw a picture, you can also subtract the coordinates. Just make sure you do the end point minus the initial point. So that's going to get you the vector. And then, so that would be what the vector would look like if we moved this endpoint to be here at 0, 0, then the other endpoint would be at 7, -7. So then the magnitude of vector xy is going to be the square root of 7 squared plus -7 squared, which is the square root of 49 plus 49, which is the square root of 98, which is ever so slightly less than 10. It's going to be 9.89, or 9.9, let's say. When vectors are represented by ordered pairs, they can be easily added, subtracted, or multiplied by a scalar. The rules for these operations on vectors are similar to those from matrices. We haven't actually done matrices because we skipped chapter 2. So ignore that bit. Yeah. Just ignore that. Not the point. So the operations for vector A, vector B, and any real number k, when we are adding vector A plus vector B, we add the x coordinates and we add the y coordinates. Subtract A minus B, you subtract the x coordinates and then subtract the y coordinates. If you multiply by some scalar k, multiply each coordinate by your scalar. Very easy. So M is the vector 5, -7, N is 0, 4, and P is -1, 3. Find each of the following. M plus P. So M plus P is going to be 5 plus -1 and -7 plus 3. Add the x coordinates, add the y coordinates. So that's going to be 4, -4. M minus N, 5 minus 0, -7 minus 4 is 5, -11. 7p means that we multiply the -1 by 7 and we multiply the 3 by 7, which gives us -7, 21. And then a tricky one, 2m plus 3n minus p. So 2 times 5, -7, plus 3 times 0, 4, minus -1, 3, which is going to be 10, -14, plus 0, 12, minus -1, 3. 10 plus 0 minus -1 is +1, which makes that 11 in the x direction. -14 plus 12 would be -2, minus 3 would be -5 for the y's. Paramedics Paquita Gonzalez and Trevor Howard are moving a person on a stretcher. Mrs. Gonzalez is pushing the stretcher with a force of 135 newtons at 58 degrees with the horizontal, while Mr. Howard is pulling the stretcher with a force of 214 newtons at 43 degrees with the horizontal. What is the magnitude of the force exerted on the stretcher? So what we need to do is we need to break these vectors down into their components. So we're adding these two vectors together, but we don't know what their x and y components are. So we have a vector. This is the first vector with a force of 135 newtons, and that makes 58 degrees with the horizontal. Mr. Howard is pulling at 214 newtons and makes an angle 43 degrees with the horizontal. The resultant vector here is going to be the sum of the x's plus the sum of the y's. So we need to break these down into the x and the y components. So if this is x and this is y, right? Remember again our SOHCAHTOA. The x is the adjacent side, so we're going to be using cosine. Cosine of 58 degrees equals x over 135, which means that x equals 135 cosine 58, which is 71.5 newtons. Y is the opposite side, so that's going to be the sine. Sine of 58 equals y over 135. Y equals 135 sine 58. Change that cosine to a sine. And I get 114.5 newtons. Now we're going to do the same thing with this vector. So again, we'll call this x2 and y2. x2 is our adjacent side. So cosine of 43 equals x2 over 214. Or x2 equals 214 cosine 43. which is 156.5 newtons. And similarly, y2 is going to be 214 sine 43, which is 145.9. And then to add these two vectors up, we want to add the x's. So x plus x2 is going to be 71.5 plus 156.5, which is 15 plus 7 is 22, 228 newtons. And y plus y2 is going to be 114.5 plus 145.9, which is 4, carry the 1, 0, carry the 1, 4, 5, 250.4 newtons. So as a vector, this is 228, 250.4. Now, the question is asking for the magnitude of this vector. We'll call this resultant vector. Call this resultant vector R. So the magnitude of resultant vector R is going to be the square root of 228 squared plus 250.4 squared. Which is 338.7. That would be the force exerted on the stretcher. And real quick, a vector that has a magnitude of 1 unit is called a unit vector. A unit vector in the direction of the positive x-axis is represented by I, and a unit vector in the direction of the positive y-axis is j. So I is the vector 1, 0, and j is the vector 0, 1. We can also represent other vectors in terms of I and j. So if x is some vector, let's use the 3, 5 again. Right, we could also write that as 3 times the I vector plus 5 times the j vector. Right, because I is 1 unit in the x direction and j is 1 unit in the y direction. So we can represent any vector as a sum of unit vectors. And that's it for 8.2. Tune in next time when things get 3-dimensional.